Welcome back, ladies and gentlemen. In this video, we are going to be opening up our discussion on 5.4, which is about equilateral and isosceles triangles. So we're taking a little bit of a breather using our triangle congruency theorems. And we're going to focus on a goal about defining the base angles theorem, talk about its corollary and its converse. And we're going to use the base angles theorem to go ahead and find missing sides and missing angles. But specifically in this particular video, we're going to go ahead and just simply define the base angles theorem, and we're going to go ahead and use it to identify angles that are congruent or sides that are congruent. So let's go ahead and first and foremost talk about our base angles theorem. Our base angles theorem identifies isosceles triangles, all right? Isosceles triangles. If two sides of a triangle are congruent, hence isosceles, then the angles opposite of them are congruent. So as you can clearly see here, we have side AC, all right? Side AC and side BA, both congruent sides. So what does the base angles theorem tell us? Well, it tells us that if that is the case, then these two angles, angle C and angle B, also must be congruent to each other. Think about it just common sense wise. The angle across from it will not necessarily be equal to this side length, but it will have the same measurement across from it on this side, right? And just kind of try your best sometimes during these theorems. Yes, the names are important, but if you really kind of try to do some more common sense with some things, I think it helps kind of take some of the craziness from learning all these names and all these different ifs and thens and so on and so forth, and use that into context when we talk about our converse of the base angles theorem. Remember, converse, we are switching our if-then statement. So our converse to the base angles theorem says that, hey, now you have two congruent base angles. You have two congruent base angles. If these two angles are congruent, the only way this works is if those two sides were congruent as well. So the original and the converse, okay? So let's take a look here at how we can put this into practice. In triangle DEF, we see that DE and DF are congruent segments. Name two congruent angles. So let's just quickly use our base angles theorem in application by being able to identify the angle opposite of ED. Opposite of ED is F, and opposite of DF is E. If that's the case, I can clearly say that F is congruent to E by the base angles theorem. And yes, I want you to write by the blank, all right? It doesn't say explain, but I want to because we're going to have to start using these in proofs. Let's take a look at one more. If HG is congruent to HK, then what two angles are congruent? Well, opposite of HK is G, opposite of HG is K, so it would be angle G, but be careful, you can't just call it K. Why? Because there's two angle Ks. So which angle K are you even talking about? HKG. HKG is the actual name of our angle. Now on the other side, we see that angle KHJ. So I want to go ahead and get rid of these markings so I don't get them confused. So now we have KHJ. So this angle right in here, KHJ, is congruent to KJH. Well, which two sides now will be congruent by the converse of the base angles theorem? Well, that would be HK and KJ. So HK and KJ. All right, so there is our converse and our original base angles theorem. In the next video, we will discuss the corollary to the base angles theorem.